What if I told you that the universe has a single, ultimate goal for everything in it, from an apple falling off a tree to a planet orbiting a star? Well, today we're diving into a physics paper that reveals that goal, and it does it by turning everything you thought you knew about time and motion completely on its head. So let me ask you something, a pretty simple question, really. If you and I each have a perfect clock, and we sync them up right now, will they always agree? Is time this universal thing that just ticks away at the same rate for all of us, no matter where we are or what we're doing? You might think so, but the answer is a hard no. And you don't need a $1 billion particle accelerator to prove it. The proof is probably in your pocket right now. The GPS that helps you find the nearest coffee shop, it only works because it accounts for the fact that time for the satellites whizzing around in orbit literally runs at a different speed than it does for us down here on Earth. To really get our heads around this, we're going to go on a little journey. First, we'll accept that time just isn't universal. Then, we'll introduce two key perspectives, the map and the traveler. We'll see how this totally rewrites the rules for speed, redefines what gravity even is, and then we get to the big one, the universe's ultimate goal. All right, first stop, time is not universal. And I gotta say it again, this isn't some cool sci-fi concept. It's the bedrock of how our modern world works. That comfortable idea we all have of a single global now that's the same for everyone, yeah, we've got to let that go. It's an illusion. So here's the absolute key takeaway. Time isn't some grand cosmic clock ticking away for everybody. It's a local variable. Just like your mailing address is unique to your house, the time you experience is unique to your clock, right here, right now. There's just no single now for the entire universe. And it turns out there are two main things that mess with how fast your local clock ticks. First, how fast you're moving, and second, where you are in a gravitational field, basically how high up you are. These two things are always changing the rate at which you experience time. Okay, so if time is all local and wiggly, how can we even talk about something like motion? This is where the paper gives us this brilliant analogy. To really get it, you need to look at it from two totally different points of view, the map's view and the traveler's view. And this right here breaks it all down. Think of the map as us, the outside observer, standing still, watching something happen. We measure everything with our clocks and our rulers. But the traveler, that's the thing that's actually moving, like a spaceship. It has its own clock and its own experience of the journey. And as you can see, they each have their own name for time, for speed, and for acceleration. They're looking at the exact same event, but they're using completely different rulers to measure it. So map time, which we'll call T, is what we all just kind of think of as time. It's what you get if you set up a whole bunch of perfectly synced clocks all over the place, like on Earth, and just watch them tick. It's our best shot at making a shared timeline. But traveler time, or proper time, now that's a whole different beast. This is the time that the traveler actually experiences. It's what the watch on the astronaut's wrist would really say. And here's the part that'll bake your noodle. This number is frame invariant. It means no matter how we look at it from the outside, the time that passes for the traveler is an absolute, undeniable, physical reality for them. And this whole map versus traveler thing, it's not just a neat philosophical trick. It has some seriously bizarre consequences when you start moving really, really fast. It completely changes the rules of the road, and it means the universe kind of has two different speed limits. Let's make this real. The paper points to this incredible experiment back in 1989 at CERN. They revved up a particle to an unbelievable speed. From their perspective, the lab's perspective, the map's view, it got so close to the ultimate cosmic speed limit. I mean, just look at that number. That is a whole lot of nines. Its speed, what they call coordinate velocity, was basically the speed of light. From the lab's point of view, it was hitting a wall. It just could not physically go any faster. That's the universal law, right? But, and this is absolutely mind-bending, from the particle's own point of view, its proper velocity was 88,000 light years per traveler year. So while we, the map, see a speed limit, the traveler itself experiences no limit at all. From its perspective, it could cross a distance that takes light 88,000 years to travel in what felt to the particle like just 1 year. Wow. So what does this mean for something like interstellar travel? This slide lays it out perfectly. Imagine you go on a 57-year round trip. Using the old school physics, you might get about 200 light years away. Not bad. But look at the traveler-centered physics. If you could maintain a constant felt acceleration of 1g, the same gravity you feel on Earth, for 57 years of your own time, you could fly to the Andromeda Galaxy, 2 million light years away, and come back. That is a game changer.
Okay, so let's shift gears from pure speed to the other thing that affects time, gravity. The paper argues that the force of gravity we feel is tied directly to that feeling of proper acceleration we were just talking about. The weight you feel right now, that's not a pull, it's a push.
General relativity totally reframes gravity. It's not some spooky force reaching out and pulling you down. Instead, big things like planets and stars literally bend and warp the fabric of space-time around them. Your natural path is to just follow that curve, to be in free fall. The only reason you feel weight is because the floor is pushing up on you, stopping you from taking that natural, effortless path. So what's gravity's secret weapon? How does it do this? It's time. It's all about time. That curvature of space-time means that time literally runs slower closer to a massive object, and it runs faster the farther away you get. A clock on top of a mountain is ticking just a little bit faster than a clock at sea level. And this quote from the paper just brings it all home. Because your head is a little bit farther from the center of the Earth than your feet are, time is passing a tiny, tiny bit faster for your head. Over your entire life, that actually adds up. Your head is measurably physically older than your feet. Just think about that for a second. So we've seen that time is local. We've seen that it's warped by speed and it's warped by gravity, and all of this leads us to a final, incredibly elegant principle that ties it all together. A new and kind of profound law of motion. Let that one just sink in. When no forces are actively pushing or pulling on something, when it's just coasting, it will naturally follow the path through space-time that makes its own clock tick as much as possible. It moves to maximize its own aging. And this is the stunning conclusion. That astronaut floating in orbit, the Earth circling the sun, an apple falling from a tree, they're all in free fall. They feel no proper acceleration, no push or pull. And according to this principle, they are all taking the one path through space-time that maximizes their own personal elapsed time. They are, in a very real sense, living the longest possible life they can. So we're left with this one last big question. If the natural default state of everything in the universe is to move in a way that makes it experience the most time possible, well, what does that tell us about what time actually is? Maybe it's not just the stage where the play happens. Maybe it's the destination.